go. All right, so we went over the homework, sections 4, 4, 4, 5, and 4, and 5.1. Now in 5.2, exponential growth models. Okay. At some point in the past, we solved this equation. All right, I'm just going through the reading in 5.2. You can follow along if you want. Somewhere along the line, we solved this equation. 200 times 0.886 to the t is 25. But at that time, we didn't know how to solve it algebraically, so we solved it graphically. Remember what this was? This was 200 micrograms of carbon-14 decaying to 25 micrograms. The question is, how long t? How many thousands of years? Is t in thousands of years? T was in thousands of years. Okay. So how many thousands of years does this take? So how did we do this graphically? How do you solve any equation graphically? If you don't know how to solve it algebraically, it's real easy. Remember, there's a lot of important innovations in graphing calculator technology that are important, right? But in this course, in pre-calculus, the two main things we use a lot is function notation, y1 of 2, y1 of 10, that stuff, right? And solving equations by doing what? Graphically. Set 25 equal to y1 or 2, doesn't matter. And set 200 times 0.886 to the t, or to the x, equal to the other y, and see where they intersect, right? So we did that because we didn't know how to do this algebraically, because we didn't know how to get rid of that t. We didn't know how to get that t out of there because we didn't know about logs. Now the question is, redo this again and get an exact result. How do you do this algebraically? How do you solve for t without graphing? Divide by 200 first? Okay. What's 25 over 200, by the way? Does that reduce? Isn't that an eighth? Right? 8 quarters is $2. You know the 25 times table, don't you? Quarters. Okay. All right, so let's divide by 200, and we get 0.886 to the t is 1/8, or 0.125 if you like. Don't forget there's a decimal here. Now, how are you going to get that t out of the exponent? That's a problem. I don't want it there. How do you make this a linear equation like we did on the last homework problem? Take the log of both sides. Now, which log do you want to use? Does it matter? Pick one. Common log, natural log. Remember, it's not natural log, it's logarithmic, didn't that be it? Common? Okay, fine. So log both sides? Fine. Be that way. Now, why don't we cut to the chase? What is the log of a power? T times log of the base. So let's just write that. You could write log on both sides as one step, and then t times log 0.886 as a second step, but y, we're too good for that. So t times log of 0.886 is the log. I'm running out of room. Hang on, I made that too big. My resolution isn't that great on the Kindle. I gotta figure this out. It doesn't match. Let's make this a little bit smaller, guys. I'm running out of room. You know, I need a smartboard because one key stroke and this is all gone. All right, so it's t. Let's make it a little bit smaller. T times log of 0.886 equals the log of 1/8. So how to get t alone? You're almost done. One more step. Divide by the log of 0.886. It's just a constant multiple of t, like mx or mt, right? Get rid of the m. This is a linear equation. Get rid of the slope. So t is in fact the log base 10, or whatever log you chose, of 1/8 over the same log of 0.886. Same base log, right? Got to be consistent there. And that's your exact answer. But what if you wanted a decimal equivalent to see how big this was? Can you do that in your head? Not really. So go to Ziggy. All right, Ziggy, do stuff. So that's going to be log of 1/8. You got it already? Divided by the log of 0.886 is about 17.180. Now remember, in the original question, t was in thousands of years. So this isn't 17 years, it's 17,000 years. So let's write this down, this answer down to the nearest year, 17,180. Is that okay? It's sort of like rounding off the three places anyway, the 180, right? So I'm going to write it that way. All right, so we get that that's approximately 17,180 years. Don't forget units in the answer. There's units in the question. In this case, years. And you're done. All right? So we know how to solve that equation in the past when it came up with exponential growth functions. Graphically, we didn't know how to do it algebraically. Now we know how to do it two ways. So that's nice, because if we can do the problem two different ways, get the same answer, that's a check. You need this. And it's nice to have the exact answer anyway. All right. Let's say you have the U.S. population is modeled by this function. We're just solving equations, really, is what we're doing. Okay? Let's say the U.S. population is modeled by P is 299 million people times e to the 0.009t, where t is years since 2006. Okay? The question is, can you tell me what year the population will be 350 million people? According to this model. I don't know if this model is accurate. How many people in the U.S. now? Isn't it about that already? 350-ish? 340, isn't it? This model may not be valid, but pretend this model is valid. It was based on data from 2006, and we're extrapolating to, I don't know what year it is. So how do you find what year we have 350 million people? What do you got to do? Plug in 350 for P and solve for T. Okay, and we solve them for T the same way as we did a minute ago. The T's in an exponent. How do you get it out of there? Use logs. Okay. So 350 equals 299 e to the 0.009t. Let's put the dot in there. Let's clean this up a little bit over here. All right, next step to solve for t. T is in years since 2006, so t equals 0 is 2006. What do you think? Divided by 299, okay. So 350 divided by 299 equals e to the 0.009t. Now, I really don't care that much which log you use to get the t out of the exponent. But since this is e to the, wouldn't it be nice and clean to use ln? Because e to the, ln and e to the just cancel nice and clean and you're done. You don't have to worry about any more logs. They're gone. So take the log of both sides but make it ln. You don't have to, but it's sort of nice here. So I get the ln of this side equals what? The ln of the other side. But what is the ln of e to the 0.009t? 0.009t. Want to cut to the chase? Right? Okay. So we sort of did two steps in one. We canceled out the e to the, right? But now there's one step left. All you got to do is divide by 0.009. Now you can do that, but realize that 0.009 is 9 in the what's place? Thousandths place. So it's 9 thousandths. How do you divide by a fraction? Like 9 thousandths. You divide by 9 over 1,000 means you multiply by the reciprocal of 1,000 over 9. So you could technically write this over 0.009, but it would not be incorrect to write 1,000 times the ln of stuff over 9. You could write it that way, just to make it clean. I like fractions, so I'm going to do that. It's 1,000 over 9 times the ln of 350 over 299. That's t. Now that's an exact answer, but I have no clue how big that number is. So I want a decimal equivalent to see how many years since 2006, was it, that this is? So drag out your trusty friendly neighborhood Ziggy. And let's do 1,000 times the ln of 350 over 299 all over 9 is 17.499 years, I guess, right? Basically 17 and a half years. Since 2006. So what year is that? What's 17 years after 2006? 17 and 6. 23. 23 and a half, right? 2020. So what's half of the year? June? 6 months? June? The end of June? What's half a year? The end of June, right? If you're starting in January? Okay. So we're talking about like in June in 2023. So let's write that down. 17.499? Okay. So I ran out. Did I have any room here? I ran out of room. Okay, so T is 17.499, and again, I rounded off to third place, so say approximately. But that means the year is 2023.499. In other words, June 2023, or the end of June. Okay. All right, so there you go. Blah, blah, blah. Good. So just solving some word problems using logs and jump. That's all we're doing. Let's see. All right, let's say you have two cities, both growing exponentially. One starts with 50,000 people and grows quicker than the other, which starts with 250,000 people. Question is, when do they have the same population? Or do they ever have the same population? All right, so let me give you these two populations, all right? What if the population in city 1 is 50,000 people times 1.035 to the t. Okay? All right, so it's growing 3.5% a year. It's like the APR model, not the continuously compounded interest rate model, right? So it starts with 50,000 people growing at 3.5% a year, right? Okay. Compounded yearly. The second city has 250,000 people in it, growing also a certain amount every year, but this time 1.6%. So how about 1.016? So make sure there's a decimal here. Make sure there's a decimal here. The question is, do they ever have the same population? Because one starts at 50,000, but it's growing faster than the other one that's at 250,000 already, but it's growing slower. So maybe they intersect somewhere. Do they ever have the same population? When does that occur, and what population is it? So how do you solve this? Algebraically now. Now, we've done stuff like this graphically. It's real easy. Set y1 equal to p1 and set y2 equal to p2 and point of intersection on the calculator. Done. Can you do it algebraically is the point. That's what this section's about. You now have all the tools at your disposal to do this algebraically and get an exact answer. And that's preferable. So what are you going to do to solve for t? Set them equal to each other. All right, good. All right, so 50,000. Where is it? Times 1.035 t to the t equals 250,000 times 1.016 to the t. And I ran out of room. And don't forget there's a decimal here, there's a decimal here. So what would you do to get t? Can you solve for t? What would you do to solve for t? This one's a little tricky because there's exponents of t on both sides. It's a little different.
250,000 or 25,000?
I meant 250,000. I lost a zero in there somewhere. Oh. You know, you had to say it. I need to make more room for this. Not enough room for this. I I don't like this eraser. I might need a different pen app. Oh God. 250,000. Okay, is that good? Those are zeros. It's still not good. All right, whatever. All right, there it is. So, what do you think? What would you do?
Put the T's together. Minus.
Get all the T's on one side, right? And get all the numbers, right? So how would you do that?
No.
Minus? No, nothing's adding, so I can't cancel by subtracting.
No.
Divide by stuff. All right, who are you going to divide both sides by? 1 point. There's a point here. How about we divide this power into this power and divide this constant into that constant? What's 50,000 and 250,000? That's fine. All right, so I'm going to write that. I'm going to say quantity 1.0. I don't need the parentheses. Forget that. Why do I need the parentheses? Okay. It's 1.035 to the t divided by 1.016 to the t equals 5. And there's decimals here. And that's an exponent. Doesn't look like it, I know. Dang it. Pretend that's an exponent. Is that useful? Does that help? Can I log both sides and be done? Maybe. There's two ways to go with this. Log it right now. Log both sides, whatever log you feel like. Because it's not a convenient base. It's not powers of 10 or powers of 8, right? I don't care which log you choose, right? Because what's the log of a quotient? That's a quotient on the left-hand side, right? What's the log of a quotient? The difference of the logs. But then the logs are of powers. So what happens to the t's? They come down. So that's not a bad way to go. Is there another way to go with this? Isn't 1.035 to the t over 1.016 to the t simply stuff to the t?
Yeah.
1.035 over 1.016 all to the t? You could do that. If you know that rule, that's an exponential rule. I don't know, why don't we just log both sides? Let's see. So if I log both sides, and I don't care which side, how about ln? Were you going to say something? Exactly what I just said. Yeah, that's what I'm going to do. I'm going to log both sides, but when I log that, it's going to be log of stuff minus log of stuff. Right, exactly. Right. So let's write that. So I'm going to say, I'm going to take the ln of both sides. So how's that? The ln of the top minus the ln of the bottom equals the ln of 5, because I'm logging both sides, right? I'm balancing equations in algebra. You do something to one side of the equation, do the same thing to the other side, right? Okay, don't forget there's a decimal here. Now this isn't bad because what's the log of a power? It's, how do you rewrite this simpler? T times ln of 1.065, 1.035, and the same thing here, right? All right, let's see if that helps. I'm going to have T times the ln of 1.035 minus T times the ln of 1.016 equals the ln of 5. And again, don't forget there's decimals here. So how to get T alone? 2 more steps. What's your favorite F word? We haven't talked about this. We haven't done a lot of algebra, actually. What's your favorite F word? 6 letters. Watch it. Factor out T. Okay, GCF. So take out T, and you're left with ln of 1.035 minus ln of 1.016 equals ln of 5. And again, the decimals don't show up, so here it is, and here it is. So one more step to get T alone. All you got to do is divide by that mess. It's a mess, but there you go. So T is ln of 5 divided by ln of 1.035 minus the ln of 1016, where the decimals are still here and here. And so let's ask Ziggy what that is. Now that's t the year, right? So apparently they do intersect somewhere. Apparently they do have the same population someplace. So we're answering question number 1. Do they ever have the same population? Yes. Question number 2, when? Let's find out on the calculator what t is. And question number 3 is, what is that population, by the way? How are you going to get that? If, say, t, I'm going to make it up, say t is 10. How are you going to figure out the population that they both have in common now? Plug it back in, the 10, right? Okay. So this is calculator time. That's an O, that's a O, that's a 3. All right, so it's ln of 5. Divided by the quantity. ln of 1.035 minus the ln of 1.016 is 85 years, say, the nearest year. All right. So, okay. So, all right. When am I going to write this down? All right. So, all right. Let's write down the answer. So, t is about 84 point. I'm going to round off to 3 places because wacky decimals. 84.949. 949 years from t equals 0, whatever it is, approximately. So now how do you calculate the population? The point is it's the same population for both. So take that number and plug it into either one. And what was the original thing? It was 50,000 times 1.035 to that number, right? Okay, so let's do that. You know what, on the calculator, how about if I do this? Let me store that answer somewhere. Store someplace. I don't know, alpha A. Alpha A. That's how you can store in memory temporarily stuff without rounding it off. You don't want to round off error, right? Then you do 50,000 times 1.0135 to the what I stored, alpha A. And so the population is, remember that city started with 50,000 people in year 0. Now in year about 85, we're at 156,202 people to the nearest person truncated, right? But what if I did that, if I plugged in the same number of years into the other population, shouldn't it be the same? It's a point of intersection that they have the same y value, don't they? Let's make sure about that. 250,000 times 1.016 to the alpha A. You know about the store key? Now you do. Is it the same? Well, what'd I do? Wait. Does it? What do they have? Do they really? Did I do something stupid?
Yeah, 0.035.
Oh, gosh. You know, I'm so good at this that I'm bad at this. So just get rid of that, like that, right? And now they should match, 96,000 something? Wait, I did something stupid. What's going on? I'm not getting the right result. They got a different answer? What'd they get? They got 86 years. I got 85 years. What? How'd I get 5 what? This year? Well, I divided both sides by 50,000. 250 divided by 50 is 5? Yeah, it is, right? Wait, what did I do? I did something stupid. I got the wrong answer.
They use log instead of ln.
Does it matter? It shouldn't matter.
Log. Instead of like you subtracted log 1.035 from log 1.016, they divided log 1.
They divided? Why? Wait, what did I do something weird? I'm not even looking what they did. They did it different because what they did was they made it all to the t, right? So t times log of blah. It should be the same thing. Thus, the city's population will be equal in just under 87 years, which is about 992,000 people. That's odd. This is strange. Wait, I did something weird. What did I do? I did the log of both sides, so it's the log of the top minus the log of the bottom, right? Then, power rule, the t goes in front. Then your favorite F word, take out the t. Am I doing this in wrong order? Like 1035 goes on top, right? Yeah. Right. Then ln of 5 over ln of...
But T doesn't equal 84.91.
Right, what does it equal?
It says that 86.
Yeah, they're getting 86. You know what? Let me check. Let's check our work. Let's do it graphically and check. See who's wrong. I'm wrong, I guess. I don't know. Jeez, you know, it happens. Yeah, I know. Well, you're saying that when you plug this into the calculator, you get that, right? You're just saying, right. But apparently they did it at different different steps, and they got a different year. They got 86.865 years. So they did different steps, which should be equivalent. So we should have the same answer. Let's see. How about we graph it? Let's do it graphically. Yay! All right. So y equals. Let's graph these guys. 50,000 times 1.035 to the, well, x, right? And then 250,000 to the 1.016 to the x. And they're saying that they meet in under 100 years and it's under 1 million people, right? So how about we say 0 to 100 years, scale of 10, and 0 to 1 million people, scale of 100,000. See what that looks like. All right, so here's the 1.035. Here's the one that starts with 50,000. Here's the one that starts with 250,000. And they intersect somewhere before 100 years and somewhere before 1 million people, right? Ugh. It's darn close. So super trace, intersect. Let's get over there. Come on. That's close enough, I guess. 1, 2, 3. And the calculator says 86, yeah. What did I do? I did something invalid.
In the textbook, they never, I think, said that to subtract each other.
But they did it different because I did the log of the quotient. They converted it to a power and then the log of the power. But yeah, it should work out the same though.
I did the same way you did. I still got 86.
Oh, you got 86.
I got 86.
Oh, did I type something wrong at this point? Are you saying, did you type this in?
Yeah, I typed in T.
And oh, then I typed it in wrong. That's all. You know, silly me. Let's see. It is 86.864 years, and it is 992,568 people if you truncate, right? But what did I do? Did I type it in wrong? What did I do? Where is it? There. What did I do wrong?
Maybe you're supposed to add.
Oh, look what I did. Okay, remember yesterday I said you can leave out the parentheses sometimes at the end, and then the calculator puts it in where he thinks it should put it in? Notice I'm missing a parentheses at the end, right? I have a parentheses around the 1.035. That's for the, oh, wait, I'm missing that one too. Oh, God. Bad teacher.
Yeah, I didn't put.
Yeah, that's right. That's wrong, right. I need the ln of this, so close the parentheses, second insert there. And then I didn't put one here for the denominator, but that one's optional. That's what messed it up, because it took the ln of all of that stuff. It took the ln of 1.035 minus the ln of, put the other ln in wrong. So you typed it in right. Good. So is it at 86, whatever? It is. Okay. So let's fix that. All right. So let's go here. All right. So get rid of. Whoa. That's a mess. That's a mess. I did all the tough stuff right. I just don't know how to type. All right. So it's 86. Get rid of all this stuff. All right, so does it match what they said? They say 86,865. Is that what I got? 86,865. That's what it is. Okay, good. All right, so give me my pen. 86. What are you doing? Go away. Give me a pen. Why don't I have a pen? Pen. Okay. There it is. Okay. 86.865-ish. Okay, but now I'm going to store that. Store STO. See the STO key above on? alpha whatever, some alpha is just a variable, alpha A, alpha B, alpha C, doesn't matter. So that I can do 50,000 times 1.035 to the A. And now I get 992,568 people. And if you do it to the other population with the same A, it should be the same amount. 1.016 to the alpha A should be the same amount of people, and it is. Okay, so let's say that, why is it doing that? Get rid of this. So P1 of that T equals P2 of that T is about 992,572? 992,572? No, 992,568. Where are they getting 572? Oh, they have round off error. See, look what they did. They have round off error. They're saying that T is 86.865, right? And then they plug that in. But it's not 865. It's 8648 something. They rounded up. So their population is too high. They have round off error. They're taking the rounded off answer for the years, 0.865, plugging that into the population and getting the wrong population. It's not 992,572. It's 992,568-ish. They're overestimating because they're using the rounded off years, and that's not correct. So I'm going to say 992,568. 992,568 approximately. So we're both wrong. There you go. Are you happy now? All right. So I got the T wrong because I can't type, and they got the P wrong because they plugged in the rounded off years, which is incorrect. Okay. So we're even. So there. All right, that's it. Do you remember the turtle problem? Let's revisit the turtle problem. Remember we said exponential growth models have a constant doubling time and exponential decay models have a constant half-life? Okay, let's see what the doubling time of the turtle problem was. All right. So if you recall, we came up with this model for the population of turtles. We said P, right, remember that thing? You're a naturalist, you threw some turtles into the wetlands, there was nobody there before, right? And then 4 years later you come by and there's 350 turtles or something? No, 300 turtles, and then 3 years later there was 450. And we got this model. It was about 175 turtles for the initial population times 1.145 to the T, so it increased 14.5% a year, right? All right, my question is, how long does it take to double? So if it starts with 175, what's double that? 350. What are you going to do with 350? To figure out doubling time, you're going to take 350 and plug it into P and solve for T. That's it. Okay, so here's the doubling time. Double 175 is 350. Let's see when the population is 350, what's T? Alrighty. So how do you solve for T? Algebraically. Again, you could always do this graphically. Divide by the 175, so you get that this whole thing is the growth rate is 2 is what it is, right? So I divide 175 into 350, I get the 2 again. All right, fine. So 2 equals 1145 to the T. Don't forget a little decimal over here. Okay. And then how to get T out of this? What do you do to both sides? Log it. All right, now again, it doesn't matter which log you use, so how about common log of 2 equals, now what happens when you take the log of a power? Bring the T out front, right? So T times what? Log of the base, which is 1145. There's a decimal in here. Okay, So how to get t alone? One more step. Divide by the log of 1.145. So t is the common log of 1.145 over, wow, that's a 5, over the common log of 2. Why is this not fitting on my page here? I did weirdness here. What happened? I don't like how this came out. Go away. Huh? Oh, did I write it upside down? Sorry. Let's fix that. Okay, so it's the log of 2 over the log of 1.145. It did it again. Why is it doing that? That's weird. It's connecting the top of the 5 with the bottom of the 5. Okay, there's a decimal here. There's a... Okay, there you go. All right, and that's an exact answer, but you can get a decimal equivalent by going to Ziggy. So log of 2 divided by the log of 1.145 is about 5 years.
You can stop there and get full credit.
That's an exact answer, yeah. Okay. Whenever you can show the work algebraically and get an exact answer, that's expected. But if you can get me an exact answer, you can also get me a decimal equivalent. That's different from, I can't do it algebraically, I'm only going to do it graphically, I only get a decimal answer. If you do it algebraically, you're getting both. All right, so no, one more step, give me both. Yeah. All right, so this is about 5.119 years, right? Okay, so you could write that somewhere, whatever. Now, all right, let me make it easy. What if it's 5? Nice, easy numbers. The doubling time is 5 years. What does that mean? It started with 175, and it got to 350 in how many years? 5. Now, in the 10th year, how many turtles should there be? 700. In the 15th year, 1,400. In the 20th year, 2,800. You're doubling it every 5 years, right? So you're doubling the amount, powers of 2, on the population, but you're changing the time linearly. You're just adding 5 every time, right? That's what doubling time is about. Alrighty. What about what about half-life? All right. Let's do a half-life question. Same way. All right. Let's say you have that carbon-14 dating stuff, right? Let's say you have, I don't know, Q, the quantity of carbon-14 is Q0, let's say 200 micrograms again, times 0.999879. Okay? Yeah, that's an 8. Okay, pretend that's an 8, okay? My question is, what's the half-life? Now, by the way, is this exponential growth or decay? It's decay because you're taking powers of a number smaller than 1, right? It's getting smaller, okay. So it's a decay rate. Now, if it's an exponential decay function, there's a constant half-life, okay? So, all right, you tell me, how do you figure this out? You're solving for t when q is 100, that's all. So plug in 100 for q and solve for t. 999,879 to the t. Let's say that's given. And so, next step to get t alone. So you get 100 over 200 is just, that's why it's called half-life. Oops, I got rid of the 200. What am I doing? Nine, 879 to the t, and there's a decimal here, right? All right, so how do you get t alone? really 2 steps left. Log both sides. So you get the log, let's say ln, because it doesn't matter, of 1/2 equals, now what's the log of a power? What happens, what does a log do to a power? The t comes in front. Same log base, don't change the base, 999,879. There's a decimal in there. And one more step to get t alone. Divide by that 999, a log of 9, right, of the whole mess. All right, so t is L1/2 over ln of point, well, let's do the 999,999,879. Okay, and there's a decimal here. And so you get about, well, let's see. Now that's, again, that's an exact answer. Yeah, assuming that the 999,879 is exact, it may not be. And so you get the ln, how about of 0.5, same thing, right? Divided by the ln of 0.999,879. You got how many years? 5,728 years, yeah.
Wait, where'd you get the 100 and 200 from?
I'm not reading the book exactly. Yeah, I'm asking the question. How do you get doubling time? How do you get half-life? So if I start off with 200, I want to know how long it takes to get half as much. Doubling time is if I started with 175, I want to know how long it takes to get to 350. Same concept. I don't like what they did there, so I changed it up. So that's about, what was it again? 5728. Well, let's say to the nearest year, 5728. Okay. So to the nearest year, 5,728 years, and that's an approximation to the nearest year. Ta-da! So again, round figures, let's say 5,000 years, right? So you start off with 200 micrograms. When do you have 100? 5,000 years, roughly, say it's 5,000 years. Then 10,000 years would be 50. Then 15,000 years, 25. Then 20,000 years, 12.5, right? So you're chopping it in half. It's powers of a half on the amount every time, but it's a linear increase on the time. 5,000 plus 5,000 plus 5,000. People get confused there, so I want to make sure that's clear. Okay. Alrighty then. That's 5.2. Any questions on 5.2? Okay, 5.3. The log function. I do examples of log function using things about pH and decibels and craziness, huh? Let's see. Yeah, that's sort of silly. They give me these silly models. I'm not worried about that. I'm more worried about asymptotes and domains and ranges and there you go. So what are they asking here? Interesting. You know what? I'm just going to go straight to the homework page in here. This is just questions about ln and log and stuff. Nothing really new here. So I'm going to stop. I'm going to start my recording here. I'm going to start previewing the homework at this point. Now, 5.4, you can skip it. I'm not going to test you in 5.4. Skip that. Okay. If you need log scales, you ever do linear graphs, linear log graphs, log linear graphs, log graphs, that stuff? Why do they do that? If the numbers get incredibly big, incredibly fast, you make the log of it instead. It's making it small. I'm not going to get into that. You can figure that out in science class if you need it. So, YouTube.